so what do we got? So we found that two Mercury years is going to give us 3 sidereal days or 1 solar day. So the 2 to 3 spin orbit resonance is connected with the fact that it's 2 years and 3 sidereal days. So what would actually explain this? Well, first of all, if we go back to the idea of the tidally locked orbit, a tidally locked orbit would mean that Mercury would be showing the same phase toward the sun at all times. The problem with that is that it actually can't happen with Mercury because Mercury's orbit is elliptical. Now, an elliptical orbit, remember, implies higher speed motion closer to the sun, right? Because this equal areas equal times law, Kepler's second law of motion. In order to prove that equal areas equal times, Mercury has to move faster in its actual speed through space, has to be faster close to the sun than it is far from the sun. Okay, so that means that Mercury's speed is changing. But Mercury's spin rate is actually the same. It's spinning like a top, so it's spinning the same spin rate all the time. So if we set things up so that Mercury's spin is such that it shows the same phase toward the sun out here, well then it's going to be spinning too slowly in here, and it won't be able to show the same phase toward the sun. Or if you set it up the opposite way and you say, okay, well, I'm going to make Mercury spin so that it shows the same phase toward the sun here, well then out here, it's going to be spinning too quickly and it won't show the same phase toward the sun. So no matter how you set it up, Mercury's spin on its spin axis is not going to adjust itself during orbit. That's just a constant spin rate. So when you have an elliptical orbit, you actually can't have a perfectly tightly locked orbit. So that's part of the puzzle here. Now, if you look at the moon, there's no problem at all because the moon's orbit is nearly perfectly circular. It's slightly eccentric, but not much. So with the moon, you can actually get essentially a tightly locked orbit, although you do get a phenomenon called the rocking of the nose, which is a little bit of a rocking motion that you see when you look at time-lapse photos of the moon, because of the fact that it's not a perfectly circular orbit. I'm not going to worry too much about that right now. All right, so what we find is that if you pick a certain point on Mercury, it's going to have a high noon every 2 years. And it's going to have a high noon every 2 years, and it's going to have midnight every 2 years. And it's going to alternate between midnight and noon as we go around the sun. But you also have the elliptical orbit. So that means that there's one point on Mercury, there's one special point on Mercury that has high noon when Mercury is at perihelion and is closest to the sun. What we find is that that particular point on Mercury that experiences high noon during perihelion actually is a special place on Mercury. It's a special place called the Calorus Basin. Called the Calorus Basin, the name Calorus is from calorie, which is from heat. And the reason we use that term is because we're talking about the point on Mercury which has high noon when Mercury is closest to the sun at perihelion. So that's going to be the hottest point on Mercury. Think about it, right? It's the point on Mercury that when noon occurs, Mercury is closest to the sun, so you're getting the strongest solar radiation. So it's the hottest point on Mercury, and that's what we call it, the Calorus Basin. The Calorus Basin actually resulted from a huge ancient impact, which we're actually learning more about now because of the Messenger mission, which has taken unprecedented levels of photographs of this exact feature. I'll show you some of those photographs in a moment. But billions of years ago, an asteroid hit Mercury at that point on Mercury and deposited a mass there, which we think the sun is grabbing hold of gravitationally whenever there's a high noon at that point. And that is the actual force that's reinforcing this spin-orbit resonance I'm talking about. We basically see a situation where if Mercury were to spin a little bit out of position, what would happen is this big mass of the Calorus Basin would be a little off the correct position, but the sun's gravity would reinforce it, pointing to the sun. And so, in a sense, it's kind of like differentiation, because the sun is trying to pull the most dense part of Mercury towards itself. So that is the actual process we think that reinforces this 2 to 3 spin-orbit resonance. So the Calorus impact actually was this impact billions of years ago, a very large asteroid, which apparently sent seismic waves right through Mercury to create what's called the weird terrain on the other side. The very weird jumbled mountain range that we see over there. So we see the Caloris Basin, which is a huge impact basin, about 1,400 kilometers across, and then we see this weird terrain on the opposite side, which is associated, we think, with the same impact. All right, so from the Mariner photos from the mid-1970s, this was the best shot we had of the Caloris Basin, which is not too much. We're not even seeing the center of it at all. But we are seeing this ring of mountain chains that formed around the Caloris Basin because of multiple layers of ejecta falling down. Now, if we go to what Messenger is able to see in the same spot, we get this breathtaking photo of the same region, the Caloris Basin. You can really see the impact clearly. There's subsidiary impacts that happened over the billions of years since that time. But actually, I also wasn't able to find a photo of the weird terrain. I'll try to find that. That should be available as well. But this is just a gigantic impact crater. And this point right here is the point that faces the sun during perihelion every other year. And remember, it's a flip-flop cycle. So when you're going to have noon at the Caloris Basin during perihelion, so it's going to be incredibly hot. But 1 year later, it'll be midnight at the Caloris Basin. Remember that red vector was flipping back and forth every year. So we're going to start off with noon, and then a year later it'll actually be midnight, very, very cold at the Caloris Basin. And then the year after that, it'll be back to high noon there. And we think there's a very large mass that was deposited there, which is giving the sun this kind of gravitational leverage to reinforce that resonance. Now, we already talked a little about the heating cycle on the moon. We saw that there was a 400-degree variation of temperature on the moon, and I made the point that we would see the same kind of temperature variation on the Earth if it were not for our atmosphere. That's the only thing that's moderating our temperature variations every day, compared to what we see on the moon, which is our traveling companion through space. So we would be seeing the same kind of temperature variation. Now, Mercury has no atmosphere, so when you're talking about Mercury, you're talking about an object that's subject to the same kind of thermal variations we see on the moon, only amplified because, of course, it's much closer to the sun. So the high temperatures are going to be much higher. So if we look at the daily temperature cycle on Mercury, what we see is variation down to about 100 kelvins. That's actually similar to the nighttime temperature on the moon. So the nighttime temperatures in the solar system are usually about 100 kelvins because no matter where you are, if you don't see the sun, you're going to equilibrate with about 100 kelvins. But whereas the moon's high temperature is 400 Kelvin, notice that on Mercury it's over 600 Kelvin. I mean, it's incredibly hot. And the surface temperature is determined by the same kind of factors that we talk about when we talk about the Earth. It's always a balance between heating and cooling. But the thing is, the heating is so much more strong on Mercury that, of course, you simply drive the temperature up. And then when the temperature gets high enough, Mercury is able to radiate enough infrared to balance the heating, and you get a stable temperature. But it's a much higher temperature than what you have on the Earth and the Moon. Okay, so the Moon and Mercury comparison again. The Moon daily temperature variations are between 100 and 400 Kelvin. They both have no atmosphere or no water, so it is kind of an apples-to-apples comparison in the sense that neither one of them has any way to moderate its temperature. So what we're seeing is a temperature cycle that's indicative of its distance from the sun. We also, of course, as I mentioned, see highly cratered surfaces, and the crater evidence is pretty well preserved on both because there's no wind or weather erosion, but there is, of course, crater-type erosion. Okay, anyway, let's just talk a little more about the temperature cycle. The 600 Kelvin high temperature on Mercury is for sort of an average location on Mercury. But it's even more extreme if you look at the Caloris Basin. Because remember, the Caloris Basin is the spot on Mercury that experiences high noon at perihelion, which is when Mercury is closest to the sun. So at the Caloris Basin, the high temperature can even exceed 700 kelvins. And yet, despite this enormous temperature on the surface, if you get close to the poles on Mercury and you look down into these shadowed craters at the poles, there's actually strong evidence for ice there, believe it or not. So you can do everything. It's the whole easy bake oven thing. You can cook cookies at the equator, and sip iced tea at the poles. So there's the makings for something. There's some kind of fast food concept. I haven't really worked it out yet, but anyway, amazingly enough, you can have ice at the poles simply because of these deep shadows. Remember, the key issue is, are you in the sun or are you not in the sun, really? Because the nighttime temperature is only 100 Kelvin, remember, that's way below freezing. But you don't get ice in the caloric basin because it's just too hot, you want to make liquid. These craters at the poles are always down around 100 Kelvin because they don't see the sun at all because of the shadows. So you actually can have ice, and we even believe water ice. So theoretically, at least, there could even be a source of water on Mercury. And we also know that the moon has ice at its poles, and that also, of course, has implications for lunar exploration because we can take that ice, it's good old H2O ice we're talking about. We dig that out of the craters, we can actually melt that and use that for water. And the other thing about water is that if you have solar panels, you can use solar panels to create electricity, to split water into hydrogen and oxygen by electrolysis. And hydrogen and oxygen comprise rocket fuel. So if we explore the moon and we have lunar bases, we can get drinkable water and we can even produce rocket fuel by combining that with electricity from solar panels. So anyway, we sort of almost finished with Mercury. I guess we'll finish that on Tuesday next week. We have plenty of time because it's still 3 weeks before the next exam. So anyway, happy Halloween, and see you next week.